In this video, we discuss how to assess predictive accuracy of a linear regression model using cross-validation. Predictive accuracy is sometimes viewed as the ultimate test of the efficacy of a predictive model. Therefore, how we evaluate the predictive accuracy of a predictive model is crucial. In classical statistics, we evaluate models with goodness of fit, which measure the prediction error on the original dataset. It usually relies on some statistics such as p-value or r-squared, as we discussed in another video. When evaluating predictive accuracy, however, we are primarily interested in how the model will perform on data not seen by the model. After all, for the data we use to build the model, we already know the values of the target variable. A model is useful for prediction only if it can make predictions on data not used to build the model. It is reasonable to argue that prediction accuracy is a fairer assessment of models, because we have to reserve some data for model evaluation and cannot use it when building the model. We need to have more data. It is not an issue when we have plenty of data, but can be tricky when our dataset is relatively small. Using predictive accuracy to evaluate models is not an entirely new idea. Professionals working on various forecasting tasks have been using it for a long time, and it has become more prevalent in recent data science development. As we shall see throughout the course, it is used extensively in predictive modeling. Before assessing prediction accuracy, we randomly divide the data into two parts. This process is called data partitioning. One portion of the data is designated as training data, which is used to feed the models. The other portion, which is not used to feed the models, is used to evaluate the different models we built. This portion is called the validation set. How exactly do we measure prediction accuracy? The answer depends on the types of predictive modeling. It is different for regression as opposed to classification. We will discuss classification in a different video. Here, we briefly discuss how we measure prediction accuracy for regression. Recall that one way to measure the error for a particular observation is the concept of residual, which is observed value minus predicted value. We can extend that idea a little bit to construct a measure of prediction accuracy. We apply the concept to the validation data by calculating the value for all rows in the validation data. To come up with a single measure, we square each residual and sum them all up. Note that the square operation is needed here because otherwise positive and negative errors cancel out. The measure we just described is called sum of squared errors, which seems to be an appropriate way to measure prediction accuracy. There are other ways to represent the same information. One alternative is RMS error, or root mean square error, which is the square root of the sum of squared error divided by the total number of rows in the validation data. Now, let's look at the cross-validation results for the housing data. We first divide the data into training and validation sets, where we take 60% of the data, or 180 rows, as the training set, and the rest belong to the validation set. We use the training set to feed the model, and we use the validation set to calculate measures of prediction accuracy. In this case, the sum of squared errors is 39326,517, and the RMS error is 558. Both of these measures can be used to compare different models, where smaller values are preferred. It is interesting to point out that the 59 is slightly different from the one we saw before. In particular, the intercept B0 is now minus 105.95, and the slope B1 is 0.4619. This is because here we only use the training set to feed the line. In general, when we use different subsets of the data to feed the model, we will get slightly different coefficient estimates. Therefore, the cross-validation result likely depends on how we split the data into training and validation sets. One way to deal with this issue is to perform what we call an n-fold cross-validation. In n-fold cross-validation, we divide the dataset by row into n equally sized sets, and run the estimation validation process n times. For each of the n runs, we use one set of the data as validation data and all other sets as training data. The overall performance measure is average across all n runs. In this way, we obtain a performance measure that tends to be more reliable. Here is a graphical illustration of 5-fold cross-validation, where n equal to 5. We divide the data into 5 approximately equal-sized portions, each called a fold. In each run, we take one fold as a validation set and the rest of the data as a training set. I would like to point out that it is common to take n equal to 5 or 10. That is, we typically perform 5 or 10-fold cross-validation. Theoretical studies and empirical results show that they usually perform better.